Have you ever wondered what really happens to oily wastewater from industries? Or how hazardous sludge is treated, reused, or safely disposed of without harming the environment? The answer lies in smart engineering design. Designing equipment for wastewater and oily sludge treatment is not just about machines. It is about sustainability, regulatory compliance, cost efficiency, and protecting ecosystems. In this video, I will walk you through how to design a complete system for collection, treatment, reuse, and disposal. Let's start with the most important step, understanding the waste. Wastewater and oily sludge are generated from industries like oil refineries, petrochemical plants, food processing units, metalworking facilities, and even ships. These waste streams are complex. They contain free oil, emulsified oil, suspended solids, dissolved organics, heavy metals, and sometimes toxic chemicals. This is why before designing anything, you must perform proper waste characterization. You need to know parameters like flow rate, oil concentration, chemical oxygen demand, biological oxygen demand, pH, temperature, and particle size distribution. Without this data, your design will fail. Now, once you understand the waste, the treatment system can be designed as a sequence of stages. Think of it as a treatment train. Each stage removes a specific type of contaminant. A typical system includes collection, pre-treatment, primary treatment, secondary or advanced treatment, and finally sludge handling. Let's begin with collection. The collection system is where everything starts, and mistakes here can affect the entire process. It includes drainage pipelines, sumps, pits, and pumping systems. One key rule is to avoid turbulence. Turbulence can break oil droplets into smaller particles, making separation much harder later. Whenever possible, use gravity flow instead of pumping. Also, install coarse screens to remove large debris early. Another important component is the equalization tank. This tank helps balance fluctuations in flow and pollutant concentration, ensuring a stable input for downstream processes. Next comes pre-treatment. This stage removes bulk contaminants, especially free oil and large solids. One of the most common pieces of equipment is the API separator. It works based on gravity, allowing oil to float and solids to settle. However, API separators are mainly effective for free oil. For better efficiency, especially in compact systems, inclined plate separators are used. These use multiple plates to increase surface area, improving oil separation. But what about emulsified oil? This is where dissolved air flotation, or DAF, comes in. DAF systems inject tiny air bubbles into the water, which attach to oil droplets and solids, lifting them to the surface for removal. Pre-treatment significantly reduces the load on the next stages. Now let's move to primary treatment. This stage focuses on removing suspended solids and residual oil. It typically involves coagulation, flocculation, and clarification. In coagulation, chemicals like alum or ferric salts are added to neutralize particle charges. Then in flocculation, polymers help these particles combine into larger flocks. These flocks are easier to remove, either by settling or flotation. Finally, in the clarifier, solids settle at the bottom, forming sludge, while cleaner water flows out. Designing this stage requires careful control of mixing intensity, retention time, and chemical dosing. Now comes secondary and advanced treatment. At this point, most solids and oil are removed, but dissolved contaminants still remain. Biological treatment is often used here. Processes like activated sludge use microorganisms to break down organic matter. More advanced systems like membrane bioreactors combine biological treatment with filtration for higher efficiency. For further polishing, filtration systems like sand filters, activated carbon filters, or even reverse osmosis can be used. This stage is critical if you want to reuse water, and reuse is becoming increasingly important. Treated water can be reused for cooling systems, irrigation, cleaning, or industrial processes. This reduces freshwater demand and lowers operational costs. Now let's talk about sludge, which is often the most challenging part. Sludge is generated in multiple stages and contains concentrated pollutants. Handling it properly is essential. The process begins with thickening, which reduces water content. Then comes dewatering using equipment like centrifuges, filter presses, or belt presses. These systems reduce sludge volume, making it easier and cheaper to handle. In some cases, sludge may require stabilization to reduce odor, pathogens, or toxicity. Recovered oil from sludge can sometimes be reused or converted into low-grade fuel. Finally, we reach disposal. Disposal must follow strict environmental regulations. Depending on its composition, sludge may be classified as hazardous or non-hazardous. It must be sent to approved treatment, storage, or disposal facilities. A good design always includes monitoring systems, sampling points, and automation to ensure compliance and performance. Now let's quickly summarize the key design principles. Always start with accurate waste characterization. Design systems in modular stages for flexibility and scalability. Optimize for energy efficiency and minimize chemical usage. Plan for maintenance and long-term operation. And most importantly, design with environmental compliance in mind, because in the end, designing wastewater and oily sludge treatment systems is not just about equipment, it is about sustainability, resource recovery, and protecting our planet. If you found this valuable, make sure to subscribe to the channel for more engineering insights, practical design guides, and real-world solutions.